Alright, welcome everybody to this week's tutorial, which is being helpfully webcast instead of being given in class because it's a holiday. So today we're covering very important topics: conditionals, loops, and functions. This is basically the core of what makes programming powerful, what makes it something that you want to learn how to do. So we're going to just go ahead and jump into it. Conditionals are basically something that allows you to create a fork in the road in your code and have it go one direction if one thing is true and go in another direction if another thing is true. Some of you had a little bit of experience with this in the homework for last week. You implemented a basic if statement if you did the bonus part of the homework. So the primary conditional is if, and when you begin a line with if, it basically creates an indented block of code. And that indented block of code will be run only if that statement is evaluated as true. So to give an example, I can say if x greater than 5, indent, print, you win the game. So basically what will happen at this point is if at this point in the code, and remember that the interpreter reads line by line, storing variables as they're created. If it gets to this line of code and x happens to be greater than 5 at that point in time, it will print, you win the game, and then keep going to the next section of code. So the syntax here that's important to remember is you have your if statement lined up with whatever other code you're writing. You end it with a colon, and then you have to have an extra indent, one indent, to have whatever's going to be inside your if statement. So to give an example, we can say, for example, x equals 5, y equals 4, z equals 2 times x plus y. So then if we said if z less than y, print this will never print. So I can write that in here because the way we've set it up, z is in fact equal to 2 times 5, which is 10, plus 4, which is 14, which is never going to be less than y. So that statement is never going to print. You can enclose as much within an if statement that you want, so it's not limited to one line. I can come here and also print something else. On the other hand, you can also have these what are called elif statements or else statements. So basically what they do is if the condition is not met, what happens? Now, if you have an if statement and nothing else, what will happen is if the statement is true, that line of code will execute, and then it'll just continue running through the rest of your code. But you might want it to do something specific if the statement is not true, or if some other statement is true, and that's where elif and if comes in. So you can say if x greater than 5, print yay, else print aw. And so you can see, like, if I didn't have this else statement there, it would print aw every time, regardless of whether it had printed yay before. So I can have this else statement to specify what happens in the case that it's not true. Now, these conditionals, you're not limited to using only one per line, so you can use and or to basically combine a bunch of them together. And you can also use shorthands like less than equals to or greater than equals to. So to give some examples of that, you can say, for example, if 2 times z is less than x squared and y is greater than x, or 3 times z is greater than y squared, then print wow. So like this is a little bit more complicated of a statement. It allows you to say, okay, well, if this complicated set of conditionals are all true, or some other set of conditionals are all true, or that sort of combination, then you'll have some sort of outcome. And of course, you could like switch these around. You could have the or here and the and here, and that would change the meaning of the statement. But it would have you then say, okay, so now either the first two conditions and the last one must be met. So yeah, elif is shorthand for else if, and basically, elif just saves you a little bit of time in indenting. For example, if I have something like if, x greater than y, print yay, and then I wanted to say else if x less than y, print y, and if x, say, equals y, print OK. So you can see what I've done here is said, if x is greater than y, print yay. If it's not, then it executes the else statement, and then it'll say, if x less than y, do this, and if x greater than y, do that. But you can see that I've required like 1 and then 2 separate indents. I can actually make this less indented by turning these into elifs. And so that's kind of how it saves you time. Else if this, and then else if that. Okay. So that's basically how you can use conditionals in your code to determine whether a line or block of code will run depending on the truth of a certain statement. And so there are other cases where you can have certain things like if some value equals true. And now true is a Boolean, it's a special data type. So you could have defined it to be true or false in some separate part of your code, and this will check if it's true. And that sort of thing. So there's all sorts of if types of things you can do. There's actually another thing you can say, like if you have two arrays, you can say if x in array or not in array. And that can also be your if statement. So it'll check whether the variable that you've called x is in a certain array or not. So loops. Loops allow us to set off a block of code that's going to be repeated over and over again under various conditions that we get to define. So the first one that's a little bit easier to understand is called a while loop. So a while loop is a block of indented code that will continue to run over and over so long as the conditional statement at the top is evaluated as true. So here's an example of that. It's a little countdown basically. So first we set some variable x equal to the number 100. And then we say while x is greater than 5, print x, and then set x equal to x minus 1. So what this is basically going to do is Python is going to arrive at this line of code. It's going to set x equal to 100. It's going to evaluate the truth of this statement, and it'll say, okay, yes, x is greater than 5. So it'll print x, and then it'll set x equal to x minus 1. And then it'll go back and check again, is x still greater than 5? And if it is, it'll keep doing this over and over. So you can see what will happen is this will print 100, 99, 98, 97, 96 until it gets to 5. Or rather, until x is equal to 6. And then once it sets x equal to x minus 1, x will now be 5. 5 is not greater than 5, so it won't print that anymore, and it'll keep going down through the rest of your code. So that leads you to sort of an important point. You have to be careful while you're defining your while loops, because if it doesn't have a mechanism within it to make sure that the conditional will eventually be broken, then your code will hang in the while loop forever. For example, if I set x equal to 100, but then I change this to be a plus, now it'll print 100, 101, 102, 103, and it'll literally keep going until you kill your computer. It brings up a quick point. If you do have a while loop that's sort of running infinitely and shows no sign of stopping because you messed something up, you can hit Control-C on your keyboard, and that should interrupt the Python process and cut to the next line. So it'll sort of quit that calculation. So we want to make sure that our while loops have some sort of minus sign in it. And when you write more sophisticated code that takes maybe 10-15 minutes to run anyway, you can actually import time modules to basically start a timer when your calculation starts, and you'll have an if statement in here that says something like if timer greater than, say, like 20 minutes or something like that, then you can use the command break, which can break you out of a loop, or you can do something like set x equal to 0, and that will then automatically break out of your while loop. So the other type of loop that we use is called a for loop. For loops allow us to iterate over a certain range of values, and there's kind of two main ways of using for loops and two main ways of thinking about them. You can iterate over elements, or you can iterate over indices. So we talked about in the previous lecture how the iterable data types like strings, lists, and arrays have element numbers assigned to each element in the array, something like 0, 1, 2, 3, 4, etc. When you're trying to perform calculations on an array, sometimes it makes sense to iterate through the array directly, and sometimes it makes more sense to iterate through a range of indices and then index your array at those indices to get out the values that you want. You can define your iterable variable to be I, j, k, whatever you want, and it only exists within that loop. So to give some examples, so here's an example of iterating over the indices. So if I have a list that has just random numbers in it, I can say for I in range 10. Now remember that range 10 looks something like this. Right? So when I type for I in range 10, what I'm really saying is for I in this array right here. And I could define this array separately. I could call this array range. Well, I wouldn't want to call it range because that's a special value, but I can call it range 1, and then I can just say for I in range 1. But it's usually faster to just, have something like this. And so basically it'll make I equal to 0, run the block of code. Then it'll make I equal to 1 and run the block of code. I equal to 2, run the block of code, etc. So we can see what will happen here. We have a couple of if statements. So if I is less than 5, print list1 evaluated at I. So what that means is first it'll take I to be 0, since that's the first element in the array range 10. That's less than 5, so it'll print list1 of 0 because I is 0 at this time. So list1 of 0 is a 1, so it'll print a 1. Now eventually I is going to be greater than 5, and then it'll be printing list1 evaluated at I minus 1. So, if I is 6, for example, then it'll say, okay, I is 6, 6 is greater than 5, 6 minus 1 is 5, and it'll print list1 evaluated at 5. And then here it'll print I squared no matter what. So one thing to keep in mind is here, we've arbitrarily called this range 10, and this thing happens to be 10 elements long. Usually you have long arrays and you don't really want to think about, how long they are when you make this range. So you can just do range len list 1, and what that'll actually do is first it'll calculate the length of list 1, and then it'll make a range going from 0 up to but not including the length of list 1, which will therefore be all of the indices of list 1. So you can also do stuff like that. The reason sometimes that you want to iterate through indices rather than the actual values in the array, for example, I could iterate through list 1 directly, but sometimes you're actually interested in what index you're looking at. So if I iterated directly through list 1, it would put a 3 into my block of code, but I don't actually know which index that is in the array right away. So if you're interested in doing some sort of code that also wants to know what index you're messing with along with what the actual value at that index is, then you want to iterate over the indices, and then anytime you want the value at that index, you just index the value for that I. There's another type of iteration. There's iterating over directly the list, and that's kind of what I mentioned earlier. So here, when I write for I in R, what it does is it'll replace I with 1, 5, 7, 4, 2, etc. The actual elements within R. and then it'll print each one squared, and then it'll say, if I not in R2, so now it'll say 1, is R in, is this 1 in here or not? And if it is not, then it'll print not in array 2, and if it is, then it'll print oh yes. So, and it'll do this for every single value in R1. So it'll check each of these to see if they're in R2 or not. So that's a good way to match lists up against each other. For loops are not limited to one dimension. You can actually sort of have a multi-dimensional for loop or a nested for loop. And the way that works is, for example, I could have one array that's an range from 1 to 100, or 0 to 99 rather. One that's a bunch of 25s. You know, this is arbitrary for no reason. And then I create an empty list like this and an empty array like that. These are just to sort of bang home the fact that appending to these types of data types is a little bit different. And then what I would type is, for I in range length of 1, and then immediately after that, for j in range length of 2, I can run some code. Basically what that does is, first it picks an I, then it picks the first j. So it'll pick the first I and the first j in these ranges. It'll run the code. Then it'll pick another j and run it again, another j and run it again. And it'll run all of the j's with the first I. Then it'll run all of the j's with the second I, and so on and so forth. So you can basically iterate through both of these, matching every single one along the way. And here I've chosen to iterate via the indices. So what I want to check here, or what I've decided to check is the value in the array of 1 equal to the value in the array of 2 at certain indices. And so I say, okay, well, if 1 indexed at whatever I happens to be at this point in the loop is equal to 2 indexed at whatever j is at its point in the loop, then you can do empty.append, and here I'm appending a list to my list. So I'm going to have a bunch of lists within lists that are going to contain a kind of a triple that will look like, you know, maybe it's the 12th index of I, the 45th index of j, and the value is 2. So what that would mean is both of these arrays have a value of 2 at these respective indices. So maybe that information is useful to you for some reason when you're working with your code. In this case, you can see that because one of the arrays is all 25s, there's going to be one time when the first array, I, is actually equal to 25, when you'll find that the two are the same. So that's for loops. It's important to keep track whether you're iterating over elements or indices, because sometimes you'll look at your code and you'll be like, this should work, and you'll realize that you refer to something as I when really it was the array indexed at I that you should have been looking at. Or you were iterating over directly like a list, and what you were interested in were the indices, and so you can't get that information. So that's the basics of for loops. You'll get more and more practice with these. Multi-dimensional ones can be a little bit confusing until you get used to them, so we'll be focusing in on a lot of these more simple arrays, but you can see how instantly the utility of Python has kind of shot up through the roof when you have the ability to look kind of through these lists, check whether things are in things, or determine, okay, if this is greater than that, then do this, etc. So the last thing I'm going to talk about is basically what we like to call functional programming, and what that comes down to is, well, what is a function? So far, I mean, you've been using functions already. Functions are built into Python or are part of a package like NumPy or Matplotlib. A function that you've used in the past includes, like, for example, if I set x equal to mp.arange of 10 and y equal to mp.sine of x. So here I'm calling two functions, arange and numpy. And again, I have to use this dot notation because I'm pulling these functions from their certain libraries. Now, what if there's something that you want to do that, you know, a function for it doesn't already exist out there or something? Then you can actually write functions yourself. And that's super handy. And most of the time when you're working on research or something like that, you know, you're trying to do a very specific task. So it makes sense to write functions to do sort of steps along the way so you don't have to do it every time. you can specify which arguments your function takes and what it returns. And that's basically what you see here. So like aRange takes multiple arguments. It takes an argument for like a stop, a start, a stop, and like a step. You know, so you define when you create your function that it takes 3 arguments. Some of them are optional. You can define if they're optional or not, and how it's going to take that. So, and here you know, sign, if you look up the documentation, it'll say input like array like. So what that means is you sign, it wants to take an array and give you the sign of every value in the array or something like that. You call functions using these parentheses, and so that's sort of like the main difference between calling functions and indexing things. When you index, you use the close brackets, and when you call a function, you put its arguments in parentheses afterwards. Now, arguments sort of make sense. It's just like sign, it has an argument space, and this is how we refer to it in math anyway. Now, the main difference between writing things as a script, as in like straight into the document and running it, versus as a function, it can be seen here. So if I had a script and I said, okay, x equals 5, y equals 7, print x plus y, it'll print 7 plus 5, and that'll be it. And the code will be done running. And this will run every time you run your code, and it'll print it every time you run your code. On the other hand, if I define a function over here, and I'm going to kind of talk about how you define a function exactly in a second, what it'll do is, okay, here I've defined a function called add, and I've specified that it's going to take 2 arguments, number 1 and number 2. I give it a colon, I give it an indent, and then I say whatever I want that function to do. So it sets x equal to num1, y equal to num2, sum equal to x plus y, and then it returns the sum. So now, if I kind of cover up this section down here and don't look at it, when I run my code, it will sort of run through this function, but it won't do anything with it. It won't try to plug anything into it or anything like that. And it's just like, you know, if you import NumPy, it doesn't automatically run every single function in the NumPy directory. And that wouldn't even make sense because you haven't specified any arguments. So basically what I can then do is I can write in my code print my function, and I'm giving it the numbers 5 as num1 and 7 as num2, and it'll print the return statement. So in this case, sum, whatever that happens to be after it's performed the calculation. The same thing is true. I can just set a variable equal to the output of my function the same way you can set y equal to np.sign x. So I'm setting var equal to the addition of 12 and 15. Now, of course, this would be a really inefficient way of doing things since there's already a sum function, but it's just to kind of, if you got into the grits of like, well, how does the sum function work? It would be something like this. You know that one thing plus another thing using the plus icon can actually get you a sum. So when you have np.sum of like an array or whatever, it'll take every single thing in the array and it'll just add them all together using this sort of, you know, notation. I don't actually have a requirement to set x equal to num1 and y equal to num2. I can actually just immediately set sum equal to num1 plus num2 and return sum. And in fact, it could be one line. I could just return num1 plus num2 if I wanted to. So this is a little bit more drawn out, but it kind of gets the picture across of like how functions can kind of work. And so sort of going off of that, the way we define functions is we use the def offset, a space, then we give our function a name. So here I've called this one average, this one age calc, this one normalize, and then we specify what arguments we want it to take. So now that brings me to a really important point, which is these variable names that you call here, array1, this should actually be a 2. These things are sort of just like representative holders. So you use them everywhere inside your function, but that's so that people can plug anything they want in and have the terms array1 and array2 adopt those values for the purposes of your array and then return average. And like, for example, here, if I want to set something equal to the output of that function, I can type something like x1 is equal to average of array 1 and array 2. And now notice that just because this returns quote-unquote a variable named average doesn't mean I have to call it average outside of my function. Outside of my function, I've set it equal to x1. So whatever this return statement is, in this case avg, becomes x1. And now you can see, like, for example, I plugged in an array that happened to have the same name as one of my arguments that I called, but this one doesn't have to, you know. I can have an array called array_2 and I just plug it in, and as long as it's the second input, it'll turn into R2 and be used in that way. And so that's why order is important. When you call a function and it has multiple sort of arguments that it can take, you have to go in the right order. So if I'm calling np.arange, I have to do the start, the stop, and the step. I can't do it in any other order or I'll get a different array out. Now some functions you can go in a different order so long as you actually specify. So you say start equals 1, stop equals 3, stuff like that. So there are ways of going in whatever order you want, but then you have to specifically go in and say which, you know, arguments you're inputting. So I just kind of wanted to go through the couple of functions that I put here and then a couple in an actual piece of research code to kind of give you an idea of how functional programming kind of works. Now, you can see here it's easy to make functions to do small things like the sum function that I just went over, but it becomes really helpful to use them on big chunks of your code as well, and that's kind of what we like to call a pipeline. So if your job in some research project was to pull some images, do some corrections like flat field and, you know, dark current and whatever, do an analysis of it and plot the output, it would be wise to write separate functions, like a function to load up the images and perform the corrections, and then to output those images that are corrected. Then another function to take as input the output from the first function, perform the analysis and output whatever data you want to plot, and then a final function to plot everything nicely. And what's nice about that is you can change the inputs of those functions very quickly and change to different files, different images, all of that sort of stuff. When something goes wrong in your code, it's easy to debug because you can check each function individually and see which function is causing the problems. So to look at some examples. So here I call a function avg or average. Again, this one wouldn't really make sense either because np.mean already exists, but I put as inputs 2 arbitrary arrays. It'll add them and divide by 2 and return an averaged array. Here is one that I called ageCalc. So the only input that this thing takes is a birth year. Now, the birth year that we want people to input is actually going to be a number. So this thing is just a variable that works for the internal workings of this function. So I have a variable called current. This here is a kind of special function which you won't learn unless you like need it, but it'll basically spit out the current time according to your computer, and it'll spit it out with like, it'll be like, you know, 13 Jan, you know, 2014 in some special like formatting. The current year, I'm indexing this for the last 4 because I know that it happens to spit out in form like that. So the last 4 digits of the thing that it spits out are the year. So I can get the current year by indexing, you know, -1 and 4. And then I set age equal to current year minus the birth year that was input, and it'll spit out an age. So here, if I ran my code straight through, it would print the output of ageCalc of 1994, ageCalc of 1975. But I could just as easily set my age equal to this and set, you know, my cousin's age equal to that, and then nothing would print, but now these 2 variables, my age and cousin age, would have within them stored the value of the output of that function. Here's a normalize function. So you did this in your last tutorial. There are different ways of normalizing a function where you can, normalizing an array, sorry. So you can divide it by the maximum value of the array, by the mean, or by the median, and these all kind of are different normalizations. If you divide by the maximum, then you'll get an array where the absolute maximum number is 1. If you divide by the mean, you'll get one where the maximum isn't really related to anything, but your mean of your new function will be 1, and here the median will be. So I make a function called normalize, and you put in a type as a string. So your only options for the string are max 1, mean 1, or median 1. You have to input a string of one of those three, otherwise the function won't return anything. And the other thing you input is an array. And here, it can be any array, whatever it happens to be named in your code, and it'll just get slotted into these spots. And then I have if statements. So if it's max 1, do this type of normalization, otherwise do these. And then finally it outputs the new array. So you can see here I set spectrum equal to some array. So this isn't a real array, but it might look like one, where it has like maybe 150 values in here that actually build the spectrum. And then you can normalize it by median or normalize it by mean like that. So this leads me to the last sort of point. So we talked a little bit about good programming practices last time, and what it means to sort of comment your code nicely. So what we can actually do is we can create documentation for this array, for this function. So what I do is I create triple quotes. Talked about you can comment like that. If you comment in the beginning of your function, it'll turn into a documentation. So I'll say a function to normalize arrays. Input. And then I'll give it a format, so like type and an array where type is either max 1, mean 1, or medium 1. Give it an output. Cool. So now what'll happen is if you're, if you've loaded this function in with your code, or you've run your code and this function is now in IPython, then you can actually use the help command, help normalize, which would look like this. And what it'll do is it'll actually spit out this documentation. And that'll teach someone who doesn't know how to use your function, oh, okay, I'm supposed to input a type and an array where type has to be one of those strings. So that's an example of a good programming practice. And so that's basically it for today. I'm going to post a couple of exercises that you can do if you're a little bit confused, and I'll be having office hours tonight if you want to talk about this lecture, talk about the previous tutorial, that sort of thing. And I can go over some of the stuff that I went over today. For loops are really important, and so it's going to be really critical that you get comfortable with them quickly. We'll be using them in the tutorial this week. So if anything didn't make sense, let me know. And other than that, I will see you guys all on Wednesday.